Up to now, we have discussed about the homogeneous equation of the higher order linear differential equations. Now let's discuss one step further of such kind of questions, that is non-homogeneous equation. Now non-homogeneous equation include two kind of solutions. First one is the previous case, the general solution or the complementary solution. The second one is the particular integral or particular solution, and for that we need to do a little bit more of the calculations and find the particular solution by different kind of methods. Now to find the particular integral, as I have already discussed, we have some good methods. First is method of undetermined coefficient, and second one is method of variation of parameters. Now we need to do that. But before that, let's see some of the properties of this non-homogeneous equation. Now non-homogeneous equation, the general solution of non-homogeneous equation is quite same as we have discussed earlier. First of all, we find the general solution, but the general solution, the thing that is added to it here is just the particular integral and all the linear combination of the previous cases. So this is all. So we can say that the general solution of any non-homogeneous higher order linear differential equation is just the complementary solution or the complementary function plus any particular solution. Generally we denote the particular solution with the capital Y of X. Okay, now again, the particular solution also follows the superposition principle. It means if we have been given some kind of solution or some kind of question, differential equation, where we have g1 of x plus g2 of x and g3 of x in such a way in the right hand side of the differential equation, then we can solve the solution of the differential equation by first just considering this first term, then second term, and then third term, then adding these all solutions, all particular solutions as we used to do in here. All right, so in this way we can find the solutions, the particular solutions, by using the superposition principle if we have a lot of terms in the right hand side also. Okay, before going further and solving the particular integral for the different differential equations, let us do some practice for the solutions of the homogeneous equation when some initial conditions are given. Again, before that, let's see how do we find the solutions for the homogeneous equation. It means the right sign is equals to 0 for different cases. First of all, if the roots of the characteristic equation are real and unequal, then how do we find the solution? Now if we have real and unequal roots of the characteristic equation, then what we do is we say the solution to be e of r1, e of r2, and so on. So in this way we find the solution, and then we form a linear combination of them and say that this is actually the general solution of such kind of homogeneous equation where the roots are real and unequal. Again, if the roots are complex root, then what we do is, for example, if we have some roots or which are in the form of alpha plus minus I beta, then we multiply exponential, or sorry, we put the value alpha in front of x to the exponential and beta in some of the trigonometric function, either cos or sine. Okay, then this is the way how we write the solution of complex roots when they are a complex root for the characteristic equation. Similarly, if there are some repeated root, for example r1 or r2, then to write the solution we just say y is equals to c1 of e to the power r1 of x plus c2, but a twist here is we put a x here and e to the power r2. If there are r3 and these all roots are equal, then we need to put another thing, that is x squared c3 e to the power r3. In this way we find the solution for the homogeneous equation when the characteristic equation have repeated roots. Okay, now I think we are good to go to solve this question. Now we have to find the general solution of this equation, and we have given some of the initial conditions here, and we have to plot its graph also and determine what happens to the solution when t tends to infinity. So first of all, what we do is we find the characteristic equation. Then after, so this is a kind of place where most of us get stuck. So this is what we do here is we break this whole large polynomial of the fourth degree into two of the polynomials where r minus 1 is one factor and r cube is one factor. So it will give us the roots r1 is equal to 1, r2 is equal to minus 1, r3 is equal to 2, and r4 is equal to minus 3. The catch here is whenever we find some root that have large number of large degrees, then it would be easier for us if we put or if we convert them into two linear into the product of two polynomials. It would be easy, and it would be easier for us to find the solutions also. Okay, so so the solution we can write in the linear combination of them in this way. But again, as we have been given with the initial conditions, we cannot leave the solution as like this. So we need to find the values of c1, c2, c3, c4 and put them in the places where they belong, and then after we get the specific solution. Now to find out what kind of curve does it make, either we can take this characteristic equation and predict the behavior of it. Otherwise we can take the solution of it and predict the behavior of this. Okay, now as we can see that when t tends to infinity, it is tending towards kind of negative. So we can say that yes, we can say that as t tends to infinity, the solution decreases rapidly or exponentially, because all the term here is exponential. And as you can see, the minus 3t, the degree of exponential, is largest here, and it has a negative sign, so we can say it is decreasing. It can be also a thing to notice. So this was all. Now in another video we will be talking about how to solve the solutions of the particular integrals. Thank you so much.